Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. So, we have been looking at the input output unit. We were just talking about how direct memory access works, and we looked at how arbitration of bus is an important aspect of DMA. So, we also looked at centralized bus arbitration mechanism, and so in today's lecture we will take a look at distributed bus arbitration mechanism, and then we will look at some interface circuits which are used for parallel and serial data transfer. So, coming to bus arbitration mechanisms. So, as we said, we have centralized and distributed two different mechanisms. In centralized arbitration mechanism, you have a centralized device which may be the processor itself, or it may be another separate device which will take care of doing the arbitration. The process of arbitration is basically determining who gets access to the bus. Okay. So, in a distributed mechanism, in the distributed arbitration mechanism, the responsibility of deciding who gets access to the bus is shared by all the devices which want to access the bus. Okay. So, there is no centralized device, but it is a distributed process. Okay. So, which means that we do not have a central arbiter, okay. And in that sense the distributed arbitration mechanism is said to have higher reliability. So, remember that you have a single centralized arbiter. A failure in the centralized arbiter indicates that the entire arbitration mechanism will fail. So, in that sense the distributed arbitration mechanism is said to have a higher reliability. So, which is the reason why many times we go in for a distributed arbitration mechanism. Okay. There are actually different types of distributed arbitration mechanisms that are used. So, we will take a look at one simple arbitration scheme to understand how distributed arbitration mechanisms are basically built. Okay, so, in the scheme that we will look at, we will assume the following. Let us say for instance that each device is assigned an ID, a 4-bit ID number, okay, which means you can have up to 16 devices, each is given a 4-bit ID number. And then when they actually for the purpose of arbitration, so we have these 4 lines which are used for the ID, and there is another line that is used which is called as the start arbitration signal. Okay. So, all the devices are connected therefore using 5 lines, 4 arbitration lines to transmit the ID, and 1 line which is called the start arbitration signal. Okay. So, what we have is something like this. So, you have a particular device. Okay. So, this device is connected to the bus, okay, by means of these signals. What are these signals? You have ARB 0, 1, 2 and 3, 4 arbitration signals, and a start arbitrator signal, okay, which is a control signal. So, you can see that you have input and output to these signals which are there for a particular device. So, to request the bus, what does a device do? So, let us look at that. Okay. So, what the device will do is, it will assert the start arbitration signal indicating that you want to start the arbitration process, and then place its 4-bit ID number on the arbitration lines. Okay. We said that every device has a unique ID number. So, a device which wants to access request the bus will start by asserting the start arbitration signal and also place its 4-bit ID number on the arbitration lines. There can be different devices which want to access the bus, therefore, each of them will again will put their ID on the bus. So, what will happen therefore is that the pattern which actually appears on the arbitration lines will be the logical OR of all the 4-bit device IDs which are placed on the arbitration lines. Okay. That is, if I have 2 different devices both wanting to get request access to the bus, both of them will assert the start arbitration signal. So, the arbitration signal will go low, and both will place their 4-bit ID numbers on the arbitration lines. Remember that the arbitration lines are shared by all of them. Okay. So, if you have a pattern like 0 1 0 0 which is put out by 1, say 0 1 0 0 would be like 4. So, device ID 4 is being put out by a device, and say 1 is also being 0 0 0 0 1 is being put out by another device. So, what will happen is that the signal that you have here will be the logical OR of both these inputs. So, 0 1 0 0 and 0 0 0 1. So, you will have 0 1 0 1 as the signal that will be there on these arbitration lines. Okay. So, using these lines now we try to find out which device can actually get access to the bus. So, let us see how that is done. So, now the arbitration process works like this. Okay. So, we already said that the pattern that appears on the bus will be the logical OR of all the 4-bit device IDs which are placed on the arbitration lines. Okay. So, now the arbitration process starts like this. So, what will happen now is each device will compare the pattern that appears on the arbitration lines with its own ID, okay, starting with the MSB, that is the most significant bit. If it detects a difference, that is from what its ID is and what is actually there on the bus, then it transmits zeros on the arbitration lines for that and all lower bit positions. That is, if it detects a difference at a particular bit position, starting from that bit position onwards and for all the lower bit positions, it will transmit zeros. Okay. So, now the pattern that appears on the arbitration lines is the logical OR of all the 4-bit device IDs which are placed on the arbitration lines. Okay. So, let us look at this with an example to understand how we will decide. Now, what will happen basically is when it puts out a 0, okay, all the devices now will compare whatever is there on the arbitration lines with their own IDs. So, the one which matches the device ID, its own device ID, becomes the master of the bus or is the one that is said to win the bus. Okay, that is basically how this process will work. So, an example will clarify it quite well. So, let us look at an example where I have two devices A and B. A has an ID 5 and B has an ID 6. Okay. So, both of them request the bus. So, what will device A do? It will put out a pattern 0101 corresponding to its ID 5. Yeah. So, the way the arbitration process works is like this. So, each device will compare the pattern that appears on the arbitration lines with its own ID starting from the MSB, which is the most significant bit. So, if it detects a difference at a particular bit position, then what it will do is it will transmit zeros on the arbitration lines for that and all lower bit positions. That is, at a particular position it detects a 0 from it detects a difference, from that position onwards it will transmit zeros on the arbitration lines. Okay. So, now the same thing will be done by all the devices, and of course, the pattern that appears will be the logical OR of whatever each device is putting out. So, now what happens is each device will also compare its ID with the information with the pattern that is there on the arbitration lines. So, the one that matches the arbitration line pattern is said to win the bus or said to get access to the bus. Okay. So, we will take a simple example to clarify this operation, this process. Okay. So, let us say we have two devices, a device A and a device B. Device A has an address ID 5, device B has an ID 6. Now, both want to request access to the bus. So, what is it that they will do? Both will assert the bus arbitration signal and put out their corresponding patterns. So, device A will transmit the pattern 0101 on the arbitration lines, device B will transmit the pattern 0110 on the arbitration lines. So, as we said, so now what will be out there on the bus will be the logical OR of these two patterns. So, you can see 0101 and 0110, you OR these two, you will get 0111. So, that will be the pattern that is there on the bus. Okay. So, the pattern that appears on the arbitration lines will now be 0111. Okay. This is the pattern that we will have. Now, for the arbitration process, we said that each device will compare the pattern that appears on this arbitration lines with its own ID starting with the MSB. Okay. And if it detects a difference, it will transmit zeros on the arbitration lines for that and all lower bit positions. So, let us start with the device A. Now, device A compares its ID 5, which is 0101 with the pattern that is there on the bus 0111. Okay. So, you can see where is the difference starting from the most significant bit position 00 it is the same, 11 it is the same. So, in this position, the second least significant bit position, there is a difference. So, what will A now put out? A will put out a pattern, okay, 0 1, and then starting from this position where there is a difference, we said it will put out all zeros. So, it will now put out a value of 0 1 0 0. Okay. So, that is what will be put out by the device A. So, as we said, it detects a difference at the second LSB position and puts out transmits a pattern of 0 1 0 0 on the arbitration lines. So, now the pattern that appears on the arbitration lines will be the logical OR of 0 1 0 0 and 0 1 1 0. What is the 0 1 1 0? This is the ID of the device B. Okay. So, when you logically OR these two, what you will have is 0 1 1 0. So, when this pattern is compared by ID by B with its ID, okay, it will find that the two match because B's ID is 0 1 1 0. So 0110 and the pattern on the bus is also 0110. So now B is considered to be the winner of the entire process. So B wins the arbitration and now B will be the one that will take over the bus. Okay. So this is one simple arbitration mechanism that can be used. So similarly there are other arbitration mechanisms which are used by different distributed arbitration processes. Okay. One very simple scheme that is used for instance in the SCSI bus is that there are 8 data lines. Okay. Let us say there are 8 data lines. So there can be 8 devices which are connected and each device is given a ID starting from 0 to 7, let us say. So now if a particular device wants to access the bus, what it will do is it will put out a signal, it will assert the signal on its corresponding data line. That is, a device which has 0 will put out a signal on data line 0. A device 1, if it wants to access the bus, will put out assert a signal on data line 1. If 6 wants to access it, it will put out on D6. So D0, D1, D6, if all the 3 are asserted, all of them can see that D0, D1, D6 are asserted and there is a set priority which is given for these devices. So let us say for instance 6 is given a higher priority. Let us say higher priority is starting from, so 7 gets the highest priority, 0 gets the least priority. So if you have requests from 0, 1 and 6 that are put out on the bus, automatically everybody knows that it is 6 which is the highest priority. So it will be the one that gets access to the bus and so the others will pull out of the race and 6 will win the race. This is another simple arbitration mechanism that is used. So like this we have different arbitration processes that can be used for a distributed arbitration mechanism and based on this the control will be given to a particular device. Okay. So, so we have looked at now centralized arbitration mechanism and the distributed arbitration mechanism. Using one of these arbitration mechanisms, the DMA controllers and the processor will share the bus. Okay. This is a scheme that we typically have in most of the systems. Okay. So now let us look at another aspect of interface of IO devices, which is the actual interface circuits that we have, okay, to connect up the different devices. Okay. So what is it that we mean by an interface circuit as such? Okay. So when you talk of an interface circuit, we talk about an input output interface. It consists of basically the circuitry which is required to connect an IO device to a computer bus. Okay. So which means you have an IO device on one side, the computer bus on the other side. Okay. So this interface circuit is something which is sitting in between. Okay. So there is one side which is the interface to the computer, the other is the interface to the device. So on the side that you have which connects to the computer, we have bus signals for address, data and some control. On the side of the interface which connects to the IO device, okay, you will have data path and associated controls to transfer data between the interface and the IO device. Okay. Now here, depending on what kind of device we have, you could have different types of interface here. Now this side of the interface, right, that is normally called as the port. That is the side of the interface which connects to the IO device. Okay, that part is normally referred to as the port. When we talk of ports, we can have basically two types of ports, one called the parallel port and the other called the serial port. Okay, so a parallel port and a serial port, these are terms that you would have typically heard of. Whenever we talk of buying a PC, we talk about what are the kind of ports it has, whether it has a serial port or a parallel port or how many parallel ports it has, how many serial ports it has and so on. So what are these ports basically? These are the interface, the part of the interface which allow you to connect to different input output devices. So we will take a short break now and then come back and look at the details of these ports. Welcome back after the break. So we were just talking about different interface circuits and the two sides that we have to the interface, one to the computer side and one to the device side. So we said that the device side interface is normally referred to as the port, and we said that there are two types of ports, the serial port and the parallel port. Okay. So the difference between a serial port and the parallel port basically is that the parallel port will transfer data in groups of bits, okay, in the form of a number of bits, normally 8 or 16, 2 are from the device. Serial port transfers and receives data 1 bit at a time. So you have a serial port and a parallel port which will allow you to do either a serial data transfer or a parallel data transfer. The processor will communicate with the bus in the same way, okay, that is this side, that is processor to the bus transfer will normally happen in the same way irrespective of whether it is a parallel port or a serial port, okay. and the actual conversion from the parallel to serial and vice versa will actually take place inside the interface circuit. So, as far as the processor is concerned, it basically transfers data to the interface circuits as parallel data transfers only. It is this side that you have the difference as to whether it is a parallel transfer or a serial data transfer. So, we will take a look at some of the details of this. Okay. So, let us take an example of a parallel port first. We will look at an input port and then we will look at an output port. So, here we are looking at a parallel input port. For illustration purposes, we have assumed that we have a keyboard connected to through a parallel interface to the processor. So, we have keyboard switches here, okay, which are connected by means of some intermediate circuitry called the encoder and debouncing circuit, and that is connected to this input interface. Now, this input interface is the one that will be connected to the processor. So, you can see that there are some kind of control signals here and some control signals here and some circuitry over here. Okay. So, we will be illustrating it with respect to keyboard, but similar circuits will be there depending on the different types of input output devices that we have. Okay, this is an input device. So, in this thing you can see that let us say for instance, let us assume that the processor is 32-bit processor, okay, and uses memory mapped IO, okay, and an asynchronous bus protocol. That is, it will access the bus when it requires by means of a request and will get access by means of a response or a ready signal or so on. So, let us look at the signals that we have on the processor side of the interface. On the processor side of the interface, we have data lines, okay, and you can see that this UD direction, that is, data flows in from the interface to the processor, because we are looking at a input port. Okay. So, this is data flows in this direction. Then there are address lines, and you can see that address lines go from the processor to the device, to the interface, and then there is a control signal, some read write signals indicating whether it is a read or write operation that needs to be done. So, in this case obviously it is a read operation, and then there are two other signals, one called a master ready signal and a slave ready signal. Okay. So, these are two signals which are used to by the processor and the device and the interface here to determine whether the two are ready for doing a data transfer. So, this is more like our handshake signals that we have talked about earlier. So, a master ready will indicate the process ready to do its side of data transfer. Slave ready indicates that it is ready to do its side of data transfer. So, when both these ready signals are there, you can have data transfer taking place between these two devices. So, on the process side we have these signals. So, on the keyboard side of the interface, okay, we have an encoder circuit, now which is responsible for generating the code for the key pressed. Remember that there are multiple switches that are available on the keyboard. So, when a particular switch is pressed, you need to have an identification mechanism to identify what key is pressed and encode that particular key and send it as the data to the interface. Okay. So, on the keyboard side you will have an encoder circuit which generates a code for the key pressed. Okay, that is the encoder circuit here. There is also a debouncing circuit that is normally used, which is used to eliminate the effect of a key bounce. Now, what we mean by a key bounce is that actually when we press a key, it is not just a single contact, mechanical contact that happens, but there may be some kind of a vibration. Okay. So, there will be multiple contacts that actually take place. When multiple contacts happen, it should not be interpreted as if it is multiple key strokes, it should be taken as a single key stroke. So, we normally have something called a debouncing circuit, this bounce that is there, that is removed. Okay. So, we called it as a debouncing circuit. So, a debouncing circuit is normally attached to the keyboard switches. So, it will debounce it and identify one particular key that has been pressed and send the data to this side. So, this is the keyboard side of the interface. And what is the data lines that we have here? You can see that there are some lines called data lines that which we. So, this line will actually contain the code for the key. Okay. And there is also a valid line. So, this valid line is the one which will indicate whether a key has been pressed or not, that is whether there is valid data available on these data lines or not. So, the valid line will change from 0 to 1 when the key is pressed. Now, when this valid signal is put from 0 to 1, what happens inside the interface circuitry basically is that the data that is there on these data lines will be loaded into this data in register. So, you can see that in the interface circuit here we have two blocks here, one called SN which indicates basically a status, which indicates whether there is valid data in the data in or not. So, status in, this is a status signal, so 1-bit signal, and then we have this register here called the data in register, okay, which is where the data actually will be stored. Okay. So, when the valid line changes from 0 to 1, the data that is available on these lines will be copied into the data in register and the status bit here will be set to 1, indicating that there is some valid data available in the interface. So, now what will happen is that when there is data available here, what the interface will do is it will now indicate that it has some data which is ready by asserting this slave ready signal. So, when the slave ready signal is asserted, it is an indication to the processor that there is data that is to be read from the parallel port. So, it will now when it is ready, it will put out its master ready, and when the master ready is put out, it will also specify what are the address from which it has to read and what is the whether it is a read operation or whatever control signal will be specified. When those control signals are specified, this device now will will transfer the data from the data in register here to these data lines, and that will be read by the processor. Okay. So, this is basically how a parallel input will take place. Now, you can see that when we do an output operation again, a very similar operation which will be actually done, only thing is now that the flow of data is from the processor to the printer. Earlier in the previous example, we had data flowing from the keyboard to the processor. Okay. So, now we are looking at processor to an output device. For example, if it is an output device is the printer, so it will go from the processor to the output device. Now, you can see here again, if you look at the two sides of the interface, okay, the processor side's interface is pretty much the same. Okay. You have similar address, data, read, write, master ready and slave ready. Only thing is the direction of data transfer for the data lines is the opposite of what you had for an input. Okay. Data transferred from the processor to the output interface. Okay. So, again we will assume the same thing, process 32 bits and uses memory mapped IO and asynchronous bus protocol. Okay. So, this part of it remains pretty much the same. Okay. So, on the processor side, data lines, address lines, control or read write line, master ready signal and a slave ready signal. On the printer side, now we can see that there is a slight difference over here. So, what is it we have? In the earlier case, we only had two signals, a valid signal and a data signal. Now, you can see there is one more signal here called an idle signal that has come up. Okay. So, you have your data lines which is used for transferring data from the interface to the printer, a valid line which indicates that you have data that you have valid data on these data lines, and then we also have an idle line here. Now, this is a status signal which comes from the printer to the interface. So, obviously, we are looking at this signal now as an indication to the interface saying whether the printer is ready to accept the data or not. Okay. So, remember we should not overload the printer. Okay. So, this idle signal is used for as a handshake between the printer and the output interface. So, this idle signal is the one which the printer will assert when it is ready to accept a character. Okay. That is saying that I am idle, therefore, now I can accept one data to be printed, okay, a character to be printed. Okay. So, when this idle signal is asserted by this printer, what will happen is that it will now cause this S out flag. Now, this is again another status flag. This status flag we are calling it as S out because it is an output interface. Okay. This S out flag will be set to a 1. Okay. When the S out flag is set to a 1, the processor now will place a new character into the data out register. Okay. So, which basically means when the S out flag is set to a 1, the slave ready will be inserted by this device. So, the master now ready will be inserted by the processor. Processor knows now that it can place data into the output interface. It will now place the data into the data out signal. Once the data is placed in the data out register, now what will happen is that the output interface will assert the valid signal and transfer the data from the data out lines onto this data bus and onto this bus over here. Okay. So, now valid line is active and the data lines are active. So, the printer now can take the data from these data lines and store it and put it into its buffer and or print it out. Okay. This is what will happen on this side for a output transfer. Okay. So, we say that the valid plus idle form the handshake lines for the printer. Okay. That is basically what we have. Again, now depending on what kind of printer interfaces we have, there are some standard interfaces and standard signals that are used. What we have looked at here is a basic mechanism which helps to illustrate the basic idea that is normally used. So, you will have some variation of this that is actually used in most of the other interfaces that we encounter in practice. Okay. So, this is about a parallel interface. Now, coming to a serial interface, a serial port. A serial port basically is used to connect the processor to IO devices that require transmission of data 1 bit at a time. So, the way the transfer will take place is that the serial port will communicate in a bit serial fashion on the device side and it will communicate in a bit parallel fashion on the bus side. Okay. So, the transformation between parallel and serial formats is normally achieved with the help of some shift registers that have a parallel access capability. What we have is something like this is what you will actually have. Okay. So, when you have serial input coming in, okay, it will actually go into a input shift register. So, this is what we are talking about as the circuit that will be there in the interface circuit. The interface circuit therefore will receive a serial input from the device, put it into a shift register. So, you all of us know what a shift register is, right. So, serial input coming in, it is stored in the shift into the register. So, then once you have enough data accumulate in the shift register, that can be shifted out parallelly into this data in register. So, now this data in register, remember, is similar to our data in register that we looked at in the case of a parallel interface. So, this data in now from here data can be shifted out to the processor, okay, by means of the D0, D7 lines and so on. Similarly, if I have a serial output interface, so D0, D7 will be stored into the data out register, okay. From the data out register, it will be shifted into an output shift register, and from the output shift register, it will be shifted out serially, okay. So, the serial input and the serial output are basically handled within this interface circuitry. The interface to the process side is still always parallel, okay. That is basically how we handle it. And when we talk about serial input and output, now we said we have a shift register. So, when there is a shift register, there is obviously also some kind of a clock that is used to control what is the rate at which data will be shifted out of this register or shifted into the register, okay. So, for that we have what is normally called as a transmission clock and a receiving clock, which will determine how fast data can be serially shifted into the interface or shifted out of the interface, okay. So, this is what we have with respect to a serial data transfer. With respect to serial data transfer, there are several standard interfaces that have been developed. One very common interface is the RS-232C, which is used for many communication links, okay, which is also called as a universal asynchronous receiver transmitter or UART. It is normally used for low speed serial devices. The basic advantage of using serial interfaces is that they require fewer wires, only one wire that is required. So, it is very convenient when you are connecting devices that are physically distant from the computer, okay. And the speed of transmission is normally referred to as the bit rate. The normal question that comes up here is when you have these different types of IO devices, okay, do we have to design different interfaces for every combination of an IO device in the computer? The answer to that is no, we normally do not do that. We normally have standard interfaces and protocols, and different devices will be connecting up to these standard devices and protocols, okay. So, we will just show you one standard kind of a circuitry that we normally have for the interfaces. So, you will have your processor and the main memory connected by means of a processor bus, and then a very common interface bus that we have is a PCI bus. This is normally used as the bus standard, which is used to connect to a processor. On the other side, on the interface side, you may have different interfaces that are used, okay, and one of the standard interfaces we have is a USB control. Now, USB, you must have heard of the USB port, which is a universal serial bus, okay. So, this port, the USB controller, can be used to connect up various devices which have a USB port. Similarly, you will have different controllers and different buses which are used, okay, for connecting up different devices. So, by having different standards of buses, different IO interfaces, different standards, different devices can all be connected to one another without having to design new interfaces whenever a new device comes up. So, this is basically how the interfaces are designed, okay. So, to summarize, what we have looked at is, we have looked at first the distributed arbitration mechanism used for DMA, and then we have looked at interface circuits. We looked at how parallel input output transfer takes place and serial input output transfer takes place. We also saw the necessary for standards and a typical example of how different standards are used inside a processor, okay. So, questions to look at today's contents. Question number 1, what is the advantage of distributed arbitration? Question number 2, what is the function of an interface circuit? Question number 3, how does the parallel interface to a printer normally work? Question number 4, why do we go for serial interface? Thank you.